So in today's video, we'll take what we've learned in the first video and we'll actually apply it to the type of problems we'll do. We're going to look at the example that we have a region that's under the graph, f of x equals e to the negative x. And we're going to look between x values just 0 to 2. The first thing we'll do is we're going to write an expression with a limit, but not evaluate it, that represents the area using right-hand endpoints. In part B, we're going to use 4 rectangles and use the midpoints to estimate the area. And then we'll do the same thing with 10 rectangles. So first thing we'll do, let's sketch a little picture of the graph. E to the negative x goes through 0, 1, and then slowly gets closer and closer to 0. So we're going to have a bunch of rectangles in here. So just in general with those rectangles, we'll be using right-hand endpoints. So wherever the right-hand side of the rectangle hits, that's where the rectangles will be drawn, just so you get a kind of a general idea. Now, where in the video, last time we saw the right-hand endpoints were an overestimate because it was an increasing function. Notice here it's different. We have a decreasing function, so the right-hand endpoints are now underestimates. So you always, in order to determine if something's an over or an underestimate, you would always have to look at it. So first we'll find our width. Remember, we often represent our width with delta x. To find that, we do b minus a over n. Well, in our case, b, our second endpoint, is 2, minus 0 over n. So our width of each rectangle, we're going to say, is 2 over n. Well, our intervals, we're going to start at 0. And then the next one, we'll add 2 over n to that. So our first interval will be from 0 to 2 over n. The next one will be from 2 over n, and when you add 2 over n to that, you'll get 4 over n. And then next we'll have 4 over n to 6 over n. And then we'll keep going, and eventually the last one will end in n over n. Now, we need to have a notation for some random one of those. The 0 is our x0. x1 is equal to 2 over n. x2 is equal to another 2 over n. So we're going to write it as 2 times 2 over n. And again, we know that equals 4 over n, but you'll see why we're going to do this, because it'll help us write the general x value. If we add another 2 over n, we now have 3 times 2 over n. If we add another 1, we'll now have 4 times 2 over n. And we probably get the pattern now, because what we're going to do is, what would a general, some random x value be if we picked xi? Well, notice our subscript, it's always that number times 2 over n. So this would be I times 2 over n, which we'll neaten up and write as 2i over n. And where that's going to come into play is that's going to be our plug-in when we end up writing our summation notation. So we'll come back and use that shortly. Well, first off, we're going to have 2n times f of our first right-hand endpoint. Well, our first right-hand endpoint here is 2 over n. Plus 2 over n of our second right-hand endpoint, which we have here is 4 over n. And then we'll keep going all the way to f of 2n over n. And the reason it's 2n over n instead of n over n, like we saw in the last video, is we want to end up being 2. So 2n divided by n is 2. Well, let's see if we can neaten this up. We'll pull out our 2 over n's. So we'll just have f of 2 over n plus f of 4 over n plus dot, 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 f of 2n over n. Well, remember, the function we are working with is e to the negative x. So this is really 2 over n times e to the negative 2 over n plus e to the negative 4 over n plus dot, 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 plus e to the negative 2n over n. So this is for any n. Well, for a single n, that just gives a approximation. If we want to know the exact thing, we want to see what our limit is as n goes to infinity. And this is what the question is asking for. So we're going to do the limit as n approaches infinity. And we'll just rewrite for right now the 2 over n, e to the minus 2 over n, plus e to the minus 4 over n, plus dot, 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 e to the minus 2n over n. And now we'll just write it as a summation. So we'll do the limit as n approaches infinity. We're doing right-hand endpoints. So our first value we actually used was x1. So we're going to let I equal 1 to start. And our last one we used was xn, because it was our nth x value. And then we'll have 2 over n times e to some power. Well, remember we had e to the negative x. And this is where that random one comes into play. Whatever that random x value was, that's what you're going to plug in for x in your summation. So we are really going to have e to the negative 2i over n. And this is a summation that represents our area under our curve. Because let's see what happens if we were to do it out. Now, you don't have to do this out. I'm just going to show you why it works. Well, when we plug in 1 for I, we'll have 2n times e to the negative 2 times 1, which is negative 2 over n. The same as what we had to start. And then you'll have plus 2 over n times e to the negative, and now we're plugging in 2, so we'll have negative 4 over n. Plus, and it'll keep going all the way until we plug the n in. We'll have 2 over n e to the minus 2n over n. So that'll represent the exact same thing. And that's all they wanted us to do in the question, is write the summation notation. So in reality, what we have here, if you're doing right-hand endpoints, we're going from 1 to n, because we're going from x1 to xn. This is our width, and then this is just our function with our general x value plugged in. So when you do further examples of this, you might not have to write out all the steps we did, as long as you write out the steps to find that general x value. So this is going to be real important to help you out to find the general x value that you're plugging in for your summation. And this is one type of question that we'll see. Now the second type is using the same thing. We're going to look at a specific number of rectangles. So we wanted to start out, we're going to do 4 rectangles. So that means n equals 4. So our width, our delta x, remember, is b minus a over n. So 2 minus 0, our b minus a, over our n of 4, which gives us 1/2. Now, I think it's sometimes helpful to write out all your intervals from 0, and since our width is 1/2, we'll go to 1/2. We'll go 1/2 to 1, 1.5, 1 to 1.5. And then we've got 1.5 to 2. And you should end up getting to your b value after the number of intervals it should be, which we had 4. Now, they want us to use midpoints here. Remember, we talked about as the rectangles get skinny, it doesn't matter what point you pick. So they might sometimes ask you to use the midpoint. So what we want to do is in each of these intervals decide what is the midpoint, because that's what we'll plug in our function. Well, 0 to 1/2 is like 0.5. 0.25 would be in the middle. 1/2 to 1, 0.75 would be in the middle. 1 to 1.5, 1.25 would be in the middle. And then 1.5 to 2, 1.75 would be in the middle. Now notice, when you go from each midpoint, it's the same jump as the width of your interval. So actually, after you find one of them, after we found that 0.25, we could just keep adding on 0.5 if we wanted to find the other ones. So we are going to start out with our width, 1/2, times f of our first one, f of 0.25, plus 1/2 times f of our next midpoint, 0.75, plus 1/2 f of 1.25, and then plus 1/2 f of 1.75. So now we're going to pull the 1/2 out. So we just have f of 0.25 plus f of 0.75 plus f of 1.25 plus f of 1.75. Now, I am okay if you jump right to this green step. If you know that the width of each of the intervals, because it's going to be the same, is going to be pulled out, you can jump right to that if you would like. Now, our function was e to the negative x. Once you have this written, you can do this easily on the calculator. Go to a new page or a new document. In a graphs page, put the function you want to work with, which we want e to the negative x. And then we'll go to a calculator page. And we'll basically type in what we had written on the paper. Just anywhere we have an f, we've got to make sure we put in f1. So we'll start out, we'll have our 0.5 out front, which is our interval, and start a parenthesis. Now, if you go to variable, notice that f1 is there. So you can just hit variable and hit enter, and that'll automatically put the f1 in for you. Then we've got to do our first midpoint, 0.25, close the parenthesis, plus go to variable, hit F1 again. That way you don't have to retype it. So that's really nice. The variable button, which is above the 9, you can do that each time. So our next one was 0.75. Make sure you close the parenthesis. Plus variable, F1. Now we're 1.25. Close the parenthesis. Plus, do your variable, do F1 of our last one, which was 1.75. And we'll close the parentheses. Now, it's helpful, I would say, double check, make sure everything looks right. Make sure you have the 0.5, your width, out in front of a parenthesis for everything. Make sure you typed in everything correct. And we get 0.8557 or so. And they didn't tell us where to round to. So we'll just say it's roughly 0.8557. Now, we're going to use the same technique for the second part, but we're going to do 10 rectangles. So when we start out, our delta x is going to be b minus a, 2 minus 0 now over 10, which will give us 2/10, which is 1/5. For our intervals, we'll go from 0. Remember, 1/5 is the same as 0.2, so we'll say 0 to 0.2. Then we'll go 0.2 to 0.4, 0.4 to 0.6, and we'll keep going all the way up to 2. Now, just like the last example, we're going to do midpoints. So it's helpful to write down what's your midpoint of each of these. So we got 0.1, 0.3, 0.5, 0.7, 0.9. We've got 1.1, 1.3, 1.5, 1.7, and 1.9. So again, remember, we're still using y equals e to the negative x, so same thing we were before. We've got our width, which now is 1/5, or we can list it as 0.2, times the sum of each of our heights. So remember I said I'm okay if you jump to this. So we'll have f of, we've got to use our midpoints in this question, f of 0.1, plus f of 0.3, plus f of 0.5. And I want to see this on your paper. This is your work. And then from here, I'm okay if you do it on your calculator. F of 0.9, f of 1.1, f of 1.3, f of 1.5, f of 1.7, and f of 1.9. And we'll go over to the calculator. What's nice about this is it's the same function, so we don't have to put anything new for f1. We'll have 0.2 as our new width. Make sure you start your parentheses. We'll do our variable button to get f1, and we'll do 0.1. Close the parentheses, plus f1 of 0.3, close the parentheses, plus f1 of 0.5. And we'll keep going. Make sure each time you close the parentheses. And once you get them all, make sure you double check that you have the pluses in the right place, that you have your parentheses out front. So again, make sure you go through and check to make sure you didn't miss anything, miss a parenthesis, miss a plus. Like I notice I am missing a parenthesis after the 1.3, and you would probably get an error or a wrong answer, one of the two. And we get about, when we do that, 0.8632. Okay, so same process, just with 10 rectangles. And here's just a view of it so you can see what, if you just look in the picture here, this is the 4 rectangle one. But this is what it would look like if you do it with midpoints. So you go to the middle of your interval, see where the height is, and that's how you're going to draw the height of your rectangle. So the middle, there's our height. That's where we'll draw the height of our rectangle through. Just like we did rights and lefts before, that's how you would determine the height if you were working with midpoints. And likewise, here's our picture for the 10. Again, in your interval, see where the midpoint is, and that's where you draw your height. See the y value of your midpoint, that's where you draw your height, and so forth. That's it for today's video. We'll see you next class period.